But there is a strong argument that glass is one of the most utilitarian and ubiquitous materials in the world today. And on the right hand side image, it actually reminded me of a little bit of a corridor. It's not actually a corridor, but you may or may not be aware of the fact that in the what we call the M62 corridor, so basically from Lancashire, Liverpool way out to East Yorkshire, resides about 80% of the UK's glass industry. That employs a lot of people and produces a lot of economic output for this country. And obviously in Sheffield, we're at the buckle on the belt, so to speak. So very, very briefly, I'm originally from East Yorkshire, so part of the belt. I came to Sheffield in 1992, quite a while ago now, as a student at the University of Sheffield, and I did my degree and PhD there. I then went off and worked in the glass industry for 5 years at British Glass and Glass Technology Services just outside Sheffield. And then I went back into academia again, first at the University of Sheffield and most recently at Sheffield Hallam. So I've been in Sheffield longer than I haven't now, which I think makes me qualify as a Sheffield lad, but maybe some would beg to differ. But I don't have a strong Sheffield accent, but nonetheless, I'm from Sheffield and consider myself to be anyway. Right, let's crack on. So we're going to take a little bit of a journey through time this evening, and we're going to start in the distant past. I don't know if you can see my mouse pointer. I hope you can. 2,000 plus years ago, and we're going to stop off at various points over the intervening years to look at some of the technological developments that have brought glass into the 21st century. Okay, so first of all, before we go into that, let's just take a moment to consider what glass actually is. It could be a solid, it could be a liquid, it could be a gas. Not quite sure how to access the chat in this view, but does anybody have any suggestions for whether a glass is a liquid, a solid, or a gas? As I say, I can't see any chat, so maybe if you just want to, yes, I can. Here we go. Okay, Andrew thinks it's a liquid. Catherine thinks it's a solid. Any more for any more? John thinks it's an amorphous solid. Henry thinks it's a liquid, basically. Okay, so some think it's a liquid, some think it's a solid, some think it's an amorphous this or that. It's a very tricky one to answer. Put on a very simple level, it is a material that has the structure of a liquid, but displays many of the physical and indeed chemical properties of a solid. And to illustrate this, just going to have to move a box on my screen so I can do this. So to illustrate this, we've got a little diagram on the right hand side here. Can I just check whether you can see my mouse pointer?
Yes, we can, Paul.
Yes, great, thanks. So let's say we have two different materials and we've heated them both to very high temperature, so they're molten. One of them is a glass, or will form a glass anyway. So let's say we've taken one of your windows and we've melted it down. And the other is, let's say, a standard metal, a pure metal like, say, copper or nickel. And as you cool that material down, for our copper and our nickel, we'll reach the melting point, Tm. At this point, we'll get a very, very large change in either volume or enthalpy. Probably volume's an easier way to envisage this in your minds. It freezes, and in so doing, it will crystallize. In addition to that, we get this very large decrease in volume associated with that change of state from a liquid to a crystalline solid. And then as we continue to cool below the melting point, we get further shrinkage, as indeed you get with most materials, not all, but most. Now that's an easy case. That's what happens with most materials when you cool them down. They will suddenly freeze, crystallize, and then the volume will continue to decrease as you cool them. With a material that forms a glass, on the other hand, we simply just keep cooling it and the volume keeps going down at the same rate. And here we're in a region where we basically have something called a supercooled liquid. So we've retained the liquid properties, the liquid structure, but we're below the point really at which that material would like to crystallize and to solidify. We continue to cool, and then we come into a range called the glass transition range. It's usually a range of temperatures, not a very hard specific temperature like the melting point. And we get essentially freezing in of that structure at this point. And below that temperature, we have a glass. Now, interestingly, the volume of the glass, and to an extent the structure of the glass, is dependent on how fast we cool. If we cool really fast through this region, we get a more voluminous structure than if we cool more slowly, which is an interesting aside. Now, before I go any further, one thing I'd like to do is kind of try and illustrate how ubiquitous glass is. So I'm willing to bet that every single person on this call is no more than about 2 or 3 feet away from something made of glass, possibly even closer. So if you'd like to have a go in the chat at what item made from glass or containing glass you have on or near your person, and I'm willing to bet that this covers everybody on the call. Okay, let's have a quick look. We've got mobile phone screen. Thank you, Catherine. Wine glass, Colleen. Excellent. Good call. Andy's glasses, light bulb, windows. Adrian's got a lamp. Anita's got spectacles, mobile phone screens, etc., etc. Windows, though it's dark. Thanks, David. Yes, so they're the obvious answers. Of course, most of us are looking at a laptop, and the screens on laptops are also made from glass. Anybody who's got fillings, chances are if those fillings were done in the last sort of 10, 20 years, that they're what's called a glass ionomer cement. So they contain glass. So you may have glass actually in your person rather than on your person. Spectacles, although nowadays the lenses, as mine are, tend to be made from plastic or polymer. A, it's cheaper, but B, most importantly, it's much, much lighter. A watch face, for example, mobile phone screens we've seen many times in the chat. So thank you very much for that. That illustrates just how ubiquitous glass is, and we just take it for granted. Road markings, Adrian, thank you. That's a very interesting one. Road markings, the paint that they put in the middle of the road contains small glass spheres, and those glass spheres they have a high refractive index, which means they bend the light, and they give a highly reflective surface, more so than you would get if you just had the paint on its own. Okay, let's move on. If my computer will let me. Oh, yes, right. Another question that I sometimes get asked, and I suspect many on this call might not be so familiar with, is that just about any material is potentially capable of forming a glass. And the critical factor that determines which materials are good at forming glasses, the stuff that we've just listed in the chat, for example, and which materials are very bad or poor at forming glasses, is all about this diagram here. So on the y-axis, we've got temperature, and on the x-axis, we've got time. And let's say at time equals 0, we're up here. We're in liquid state. We're above the melting temperature for whatever that material is, and we've got a liquid. Now, as soon as you cool below a critical temperature, which is this red line here, the melting temperature, in some systems that's called the liquidus temperature, but basically it's the temperature above which everything is a liquid. Once you cool below this temperature, you get into this supercooled liquid region. And where we don't want to go if we're trying to make a glass is this region where crystallization happens. Now, for some materials, the time distance between here and here is incredibly small. And for other materials, the time distance is pretty large. So those materials that we've discussed earlier, your phone screens, your windows, etc., they're very forgiving in terms of getting through this supercooled liquid region to form a glass, it's a bit like crossing a busy road. If you can run really, really fast, you can probably get across the road without being hit by anything. But if you saunter across, there's more chance of being hit by something, and that's the analogy for crystallization. Now, unfortunately, I'm not able to see you in person because I've got a few props that I would have very much liked to have shown. One of which is glass steel, and this was given to me by an industrial partner who asked that I don't reveal who they are, although some of you may wish to hazard a guess, which is steel, but it's been made in the form of a glass. It's been cooled through this region incredibly quickly, of the order of hundreds of thousands, millions of degrees a second. And in so doing, it's formed a glass. Now, it doesn't really look any different to other metals. It very much looks like aluminium foil. It's been produced very thin because that was necessary to get the heat out. But it looks very much like steel foil would if it was crystalline. But the key difference is it has the structure of a glass. So most materials can form a glass. They're capable of forming a glass if you can get across this busy road before something hits you. Crystallization. Okay, let's try and move on. Right, that's better. So the cooling rate is king. And one area where there's been an awful lot of development in even the last 10 or 15 years is in so-called metallic glasses. And more importantly, so-called bulk metallic glasses. Now, to use the diagram that I've just shown on the previous slide, for a metallic glass, which you could argue includes things like glassy steel, we need an incredibly fast cooling rate to avoid this crystallization region here before we get below TG. And consequently, this critical cooling rate for conventional metallic glasses is of the order to 10,000 to 1,000,000 Kelvin per second. That's ridiculously fast. More recently, the so-called bulk metallic glasses have been under development, and these tend to be a very complex mixture of very exotic elements, increasingly less so as time goes on. But hopefully you can see here that the critical cooling rates for bulk metallic glasses is much more forgiving, and consequently we're able to make bulk type shapes from these materials. And they display some very, very interesting electrical, structural, magnetic behavior, which lends themselves very well to certain applications. And then even more forgiving are certain polymers, and then our traditional oxide glasses, mobile phone screens, windows, etc. You can see the critical cooling rate here is very, very slow. In fact, some large telescope mirrors, for example, which are oxide glass, they're cooled incredibly slowly in order to anneal out any thermal stresses. Fortunately, they can do that with these very slow cooling rates. So cooling rate is king if you want to make a glass, but you can do it. You can make a glass out of just about anything within limits. Okay, there are various definitions of glass that you can find on the internet or in other places, and I'm not going to read all of this out, don't worry. My personal favorite is my colleague, Professor Adrian Wright, who's one of the godfathers of glass science. And his definition of glass as being an inorganic material that has been quenched from liquid to a rigid state without crystallizing. I would like to remove the in from inorganic because I think a number of organic glasses also exist. So I would say any material that has been quenched from the liquid to a rigid state without crystallizing. You may have your own definitions. You may agree or disagree with what I've said and what others have said. Okay, fundamentally, what's the difference? Well, this cartoon, I hope, helps illustrate what the key differences are between a glass and the equivalent crystalline material. So the basis of most of the glass that we're looking at on our screens, on our mobile phones, is sand, silica, SiO2. So in this diagram, each of these black dots is a silicon atom, and each of these white dots is an oxygen atom. But because it's a three-dimensional structure in real life, if you can imagine there's another one of these white dots sitting directly above the black dot. But for the sake of this cartoon, let's say each black one is bonded to 3 white ones, and each white one is bonded to 2 black ones. Now, in a crystal, you have this long-range repeating structural ordering. So the environment that this black atom here finds itself in is pretty much the same as this one, or this one, or this one. Now, in a glass, we've avoided crystallization. So this long-range order, this repeating structural unit order that's been able to establish itself isn't there. Now, on a local level, we still have the same rules. Each black one is bonded to 3 white ones. Each white one is bonded to 2 black ones. But the bond angles, and more specifically the bond rotations, are not aligned in the same way as they are in a crystal. So you get a structure that looks very much like this. Now, which of these is more efficient? Which of these gives us better atomic packing? The crystal on the left or the glass on the right? Let's see what we've got in the chat. Okay, crystal, Catherine, thank you. Anybody else? Anybody agree or disagree with Catherine? Okay, I think the eyes have it for crystal. Yes, much more efficient packing of the atoms in a crystal. You can see there's these very large, what appear to be voids regions. So if we just go back a couple of slides, if my PowerPoint will behave itself. So you remember we were looking at this diagram? The volume of the glass is greater than the volume of the corresponding crystalline material. Why? Because the atomic packing is less efficient. Okay, but on a structural atomic level, that is the basic difference between a crystalline material and its glassy equivalent. Excuse me. Now, it gets a little bit more complicated than that when we start to add other components into our glass. So for example, windows, there are 3 principal components: silicon oxide, sodium oxide, and calcium oxide, which I've not illustrated here. But when we add these other components into traditional sand-based silicate glass, you get some strange structural changes, and the sodium ions basically go in and they break up this 3-dimensional interconnected silicate network. Now that's good if you're trying to make glass, because it means you can melt it at a temperature that is more suitable for modern manufacture. Pure SiO2 has a melting temperature of about 1750 degrees C. But in order to form it into shapes, you'd have to go even higher, 2000, 2100, 2200 degrees C to be able to form it into shapes. And consequently, it's extremely expensive to manufacture with. It's a shame, because otherwise it would be perfect. So we add in these extra components that break up this 3D network of the silicate units. And in so doing, that helps them to move around and flow over one another more easily. And that means we can reduce the melting temperature and still form shapes. And so typical glass melting tanks for window glass, bottle glass, that kind of thing, are operating at 1500 plus or minus 50 degrees C, which is a lot more economically viable. Okay, so I'm a glass scientist, glass technologist. What does that actually mean? Well, basically it means I'm interested in 3 things. I'm interested in the composition of the glass, which chemical elements are used to make it up. The structure, how these constituent elements are arranged. And finally, properties, how the glass and why the glass behaves in the way it does. And so this triangle of composition, structure, properties will, I'm sure, chime with a lot of the material scientists who are listening in. This is one of the foundation stones of good material science: composition, structure, property relationships. And having an understanding of these helps us tailor and develop new glasses for new applications as well. Right, so I promised you a trip through time, so let's jump in our time machine. Now, you can take your pick. You may be an H.G. Wells fan, you may be a Whovian. For me, it's always got to be the DeLorean. But let's jump in our time machine now and start way back in Antiquity. So we're going to look at this period, sort of ancient, the ancient period up to about 2,000 years ago and beyond to maybe 500 years ago. So within this period, the very earliest glasses that we know of are these things: natural glass, basalt glass, which was fashioned into things like arrowheads and spearheads, and also happens to kill dragons if you're a Game of Thrones fan, by the way. Some ancient Assyrian and Mesopotamian beads with glazes, glass glazes, and some very ancient marbles being other examples from this prehistoric era. And then more recently, we move into the Roman era, and I'm going to stop off at the Roman era and talk about Roman glass in a moment. Romans were the first to really mass produce glass, and we'll look at how they did that in a minute. Moving forwards again, the obvious, very famous stained glass windows of the medieval period. Some really amazing glass science and glass technology went on there. And then I've put this little cup here. This is going to come in and out later in the talk, but this is what was called a forest glass. Now, the clue is in the name. It was made in the medieval period in parts of Europe, and we'll come back to the forest aspect of that later. So how did ancient glass get made? Well, basically you needed 2, 3, or 4 of these things. So first of all, you needed a very good source of sand. It needed to be relatively pure, free from impurities, and of course available in the quantities that you needed. And last but by no means least, it needed to be consistent. The second raw material that was used was a natural evaporite called natron, and this was found only in certain places, particularly in the Middle East. There are parts of what is now I think northern Egypt and the Levant area where these evaporite deposits were found, not entirely dissimilar to the salts that you find in, say, the Dead Sea, for example. And these were sodium carbonate, sodium hydrogen carbonate, sodium chloride mixtures, but key thing is they were rich in sodium. We looked at the effects of sodium earlier. Another one was seashells. Seashells are essentially limestone calcium carbonate. Now, there is some conjecture in the literature whether seashells were deliberately crushed up and added by, say, the ancient Romans to make their glass, or whether it was simply smashed up seashells that were present in the sand that the Romans were using, as you might reasonably expect. So there's still some debate over which it is, whether it was deliberately added or whether it was just present in the sand. Now, over time, the natron deposits either wore out, or a series of political and civil war events meant that these deposits were much more difficult to get to and more expensive, and increasingly people started to use plant ashes to make glass as a source of the alkali to replace the sodium. And we'll come back to this later, but the ring of stones here kind of reminds me to mention that the Pliny the Elder, in I think it was either AD 79 or BC 79, a very long time ago anyway, wrote about the origins of how glass was discovered. And the story goes that some sailors had become shipwrecked, and on the shore they built a fire to keep them warm that night, and their cargo was this stuff, natron. So they had these blocks of natron that they arranged around their fire like this. And the next morning, they noticed that where the natron and the sand had come into contact, a glassy deposit had formed. They'd melted together to form a glass. Now, how true that is, we'll never know, but it certainly has a ring of truth in it. And indeed, if you took blocks of natron and put them next to some sand and heated them up to probably of the order of 6, 7, 8, 900 degrees C, you could probably start to form a glass. So it's certainly conceivable. Okay, so I mentioned that the Romans were the first to mass produce glass, and they did it through two systems. The first system was the invention of, if you look at this red arrow here, the invention of this thing, the blowing iron. Glass blowing was invented by the Romans, and it enabled them to form shapes more rapidly and more consistently than previously possible. And so you can see this artist's impression of a Roman workshop. You've got a small furnace here that's being used to heat the glass, and you've got working areas here where the glass blowers are fashioning glass vials and glass bottles and so on. You've got other people maybe doing very early quality control. And a very interesting point is these things here, these baskets. Now, to the untrained eye, that looks like broken glass. Well, that's exactly what it's supposed to be. There are, or have been in the past, two different models for how the Romans made glass, but also transported it across their vast empire. And these two models were centralized versus local production. So in the first model, the centralized model, you had these big centralized facilities, few in number, simply there to make what was called raw glass. All they were doing was melting the raw materials together to make glass. They weren't forming it into shapes or anything. They were just making glass. A bit like our recycling bins now. The other model said that the glass was both melted from raw materials and then formed into shapes on a local level. So this model here favors the centralized model, and there have been archaeological finds over the years. This is a reconstruction in this photo, but it reconstructs what was actually found, and they found these sort of ceramic amphora, I think that's the right term, containing raw glass, which is a very strong indication that the centralized production model is probably more likely to be correct. So the glass was made in certain centralized places, transported all the way across the empire in these things, and then reworked, remelted, and formed into shapes on a local level. One example of some work I was involved in a number of years ago, this was a collaboration with Caroline Jackson just up the road at the University of Sheffield, with whom I still collaborate to this day actually. And Caroline's a glass archaeologist, and we were looking at some glasses that had been excavated in York from about the same era, about AD 0 to AD 200, so pretty old. And the samples came from the first mass-produced so-called blue-green bottles, these things. And these have been found across what was the Roman Empire. And a couple of questions we were asking were, how well did the Roman glassmakers control color and control the working properties of their glass? So, for example, what furnace temperatures and melting conditions were present, and were they consistent? So we applied several modern techniques to that. We looked at the chemical composition of the raw materials. We looked at the color and the optical properties, which tell us something about the furnace conditions perhaps. And then we looked at thermal properties, so the viscosity, how fluid the glasses were when they were heated up. Now, very complex analysis here, which I'm not going to read out, and there won't be a test at the end, don't worry. But I've highlighted a few key components in different colors. So that the main components are these ones in yellow: silicon dioxide, calcium oxide, and sodium oxide. Now, these are 5 different samples from 5 different bottles from 5 different places within the Coppergate site. But hopefully you can see that, with the possible exception of this last one here, the chemical compositions are incredibly consistent given the technologies of the era. Second thing to look at is this box in red down here. Now, you don't need to worry too much about this, but what this is telling us is that the temperature required to get a given viscosity of the glass, again, was incredibly consistent. 1395, 1407, so within 10 degrees C. So what that's telling us is that the Roman glassmaker had an incredibly consistent raw material to work and to form shapes out of, and that would have made their job much easier. The alternative was, if there was great variability, then one item to the next, the Roman glassworker would have less or more time to do things before it cooled down and they had to reheat it and so on. There's also several other interesting components. Iron, for example, which causes a blue-green color. Well, the iron content's quite variable. Other things in there that tell us something about the melting conditions, things like manganese, sulfur, chlorine, antimony, and we'll come back to those later. All of these give us clues as to how the glass was made. So first of all, viscosity. I mentioned that the melting temperatures and the forming temperatures are incredibly consistent, and this graph shows that. So we've taken modern models for mathematical models for the glass viscosity, and having analyzed the composition, we're able to predict what that viscosity would have been without having to remelt it. And we were able to conclude not only that there was this amazing consistency of working properties, but we were also able to suggest temperatures for the furnaces that the Romans would have been using for reworking the glass of being in this range, about 1000 to 1150 degrees C. And all of this just from some small samples of glass that we analyzed. We can go further still by looking at all of these different colorants. So tend to be transition metals, things like iron, manganese, a bit of copper, cobalt maybe. We can estimate the ratio of different redox states of, for example, iron, which can exist as iron 2+ or iron 3+, each of which gives different colors. But that in itself tells us something about the melting conditions, whether the melting conditions were oxidizing or reducing. There's also the presence of the antimony that I mentioned earlier, which was often referred to alongside manganese as so-called glassmaker's soap. If you chuck a bit of this in, it reduces the amount of color, and it does that by turning the iron 2+ into iron 3+. So this is telling us that not only did they exert control of the raw materials, of the glass, the composition, the viscosity, they even exerted control on the color. And they were able to get incredible consistency of color as well as all of these other amazing properties. So the Romans really were the world's first true glass technologists. Sulfur is another component. Sulfur is another component that, by measuring the amount of sulfur that's present in a glass and linking that to the color, it can tell us something about the furnace atmosphere. And to illustrate that, usually if you go shopping, you'll see amber glass, you'll see kind of an olive green glass for some wine bottles, and then you'll see our sort of standard clear and slightly blue-green glasses. And depending on the sulfur content, you will find, for example, a dark amber tends to have a sulfur content which is pretty high. These olive green wine bottles, have very low sulfur contents. And this is because the sulfur solubility in the glass is essentially determined not only by the chemical composition of the glass itself, but by the atmosphere used to melt it. So by measuring the sulfur content of our glass, which was about 0.22, call it 0.2 to 0.3%, we know it's not an amber, so we can't be here. So lo and behold, we've got some information on redox conditions, -3, which is a mildly reducing melting conditions. So the conclusion we can reach is that the Romans were extraordinarily good glass scientists and technologists, particularly given the range of techniques available to them at that time. Right, time is moving on in more ways than one. So let's move forwards in time. So from about 500 years ago, the ancient Venetian glass melters on the island of Murano. I don't know if anybody's ever had a chance to visit it, but if you do get chance, once the COVID restrictions lift a bit, I would strongly recommend it. Anybody with an interest in glass making, Murano is an amazing place. And they still make a lot of glass there to this day. But the Venetians had a secret, and they didn't like to share that secret. Indeed, people could only leave the island of Murano, the glass workers, with a special pass. If they didn't have a special pass, it was on pain of death. And that led us to something that I'm going to talk about on, I think, my next slide. So I'll leave it for a moment. But moving forward in time, we started to develop new ways of manufacturing large volumes of glass. For example, so-called plate glass, where you have a spinner. And the glass maker would spin the glass on this. If anybody's ever been to an old pub, you can sometimes see the windows in an old pub where you've got this kind of weird circly bit in the middle. Does anybody know why you get those in old pubs? Let's see the chat. Anyone got anything in the chat? The middle of the disc, Catherine, spot on, brilliant. I can see I've maybe missed one or two questions from earlier. Yes, so this spinner, the middle bit was the cheapest bit. Nobody wanted to buy it, so they'd sell it at a lower cost, and people would use it for things like windows. Moving forwards again, we have the automation of glass making, and the Owens, Illinois, or what is now the Owens, Illinois company. Originally, Mr. Owens invented this, the IS machine, the individual section machine. And this is basically what allows for mass production of bottles, jars, etc. on a vast scale. Let me just check the chat, see if there's... I bet they make them at premium price now, Henry. Yes. Ironic. If you could get your hands on one of these now, it probably would command top dollar indeed. So it was in this period that we really went for higher quality glass and truly sort of modern standards of mass production. So let's try and move on again. If my laptop will let me. Oh, yes, right. Sorry, there's a delay when I press advance, so my apologies for that. So I mentioned the ancient Venetians. This is the island of Murano, or should I say was, and they were famous for producing this stuff, so-called cristallo, or crystal glass. Very, very, very high purity, very, very white glass, you know, no coloration or very little, and it was very, very highly sought of and commanded very high prices across Europe. Now, in the 1600s, the mid to late 1600s, an Englishman called George Ravenscroft, who'd spent a lot of time in Venice and Murano, came back to England. Now, it's a moot point whether he took more of the Venetian secrets with him than he should, or undoubtedly he will have learned a lot in Venice, but he's well known for being the inventor of lead crystal glass. So he took the step of adding quite considerable amounts of lead oxide into the raw material mixture to give this very bright, lustrous glass, which mimicked or mirrored, or some would argue eclipsed, the cristallo of the Venetians. And lead crystal then became, you know, one of the major types of glass. Even to this day, you can still buy lead crystal decanters. It has that feeling of quality, both in terms of its weight, its heft, and in terms of its brightness, its lustrousness. And that really is due to its high refractive index. So when light crosses a boundary between two different media. For example, in this case, we have a diamond. All materials have an inherent what's called refractive index, which is basically the amount by which they bend the light. But you can see that the light is bent when it passes into that medium. An analogy would be if you're sitting with your legs in a paddling pool. If you look down at your legs, they seem to be going off at weird angles. And that's because the light is bent as it enters and then leaves the water. But the amount by which the light is bent, and also the dispersion, so you can see the amount by which the light is dispersed in this figure here, is a function of the composition and the structure of the material. And if you look at this diagram here, you can see that lead crystal has a refractive index that isn't much lower than that of diamond. Now, normal window glass is right down here somewhere, about 1.5. So lead crystal glass, when you cut it as well, you add in extra surfaces, so you get more of this behavior going on. So you get this very bright, lustrous behavior, and that's essentially why lead crystal looks as bright and shiny as it does. Or is it? Is it the only reason? Well, no, it isn't. One little known fact is that, again, like some diamonds, lead crystal glass actually is a fluorescent material. And what it actually does, albeit on a very inefficient scale, is it absorbs quite strongly in the ultraviolet. But a very small fraction of that absorbed radiation, it undergoes, we lose a bit of energy basically, and it undergoes something called a Stokes shift, which means that what was ultraviolet radiation is actually re-emitted as visible radiation that we can see in the sort of green-yellow region. Now, again, this is a very inefficient process. It's not been optimized or anything like that. And it's not sufficiently strong unless you use a very, very strong UV source like we did here to see it with the naked eye. But this is a lead crystal glass that we've remelted into a disc in our lab. And basically we put a UV light on the side of it, and it glows a beautiful blue color. Now, that is another contributing factor to why lead crystal glass looks so bright, because a tiny fraction of the light is being absorbed in that is being absorbed in the UV is actually being re-emitted at visible wavelengths, which we can see. Right, how are we doing for time? Must move on fast. Let's move into the last 100 years then. And this is the era of mass production of flat glass, cooker hobtops made from glass ceramics, optical fibers, and of course our ubiquitous mobile phone screens even. So this is a view into a modern 20th century and indeed 21st century, but this was taken in the 20th century, glass furnace. So these are jets of burning gas coming down from above. And here we have what appears to be little islands, and these are unmelted raw materials surrounded by liquid phase. This is where the raw materials are melted, and this will gradually move down the tank this way until it's homogenized. You've got a good quality glass melt that you can then take out and form into shapes. Now, float glass is probably the biggest single innovation in glass science and technology of the last 100 years. And it's a process that was developed by Pilkingtons in the 1950s and early 60s, but mostly in the 50s. And prior to that, it was very difficult and expensive to make glass that was perfectly flat and had a good finish on both surfaces, mainly because one of the surfaces had to be in contact with something, and in so doing that introduced imperfections, defects, and so on. So what Pilkington came up with was the idea that if you take your glass melt, so it's coming out of that furnace that we've just looked at as a ribbon, and that it enters this zone, and in this zone you've got a tin bath. So it's molten metal tin, but the temperature of that molten tin changes from this end to this end. So when the glass enters at this end, it spreads out nice and thinly, and it continues moving down here, but the temperature is cooling down as we move down through here. So the glass is getting stiffer and stiffer and stiffer. On the other hand, the tin is molten. Its viscosity may change a bit, but here it's a molten liquid with very low viscosity, and it's still the same here, more or less. So what that means is that when we get to this point, we can actually lift the glass off the tin bath without carrying any tin with us, and the glass will hold its shape. After that, it goes into an annealing layer. This is where thermal stresses that have developed are relieved. If you don't do this, there's a good chance of spontaneous explosion of the glass later on in its life. Remove those thermal stresses, and then it's simply cut, stacked, coated if necessary, and shipped. And it was this idea of floating it on a bed of molten tin that was the true innovation, and that is now how well over 95+% of the world's flat glass is made to this day. Okay, moving forwards again, I'm conscious of time, into the 21st century. So we've talked about mobile phones. Many of you may recognize this, Gorilla Glass. Now, Gorilla Glass is what is on the face of these things, iPhones. This is a very old one, by the way, but it's still got Gorilla Glass. Does anybody know why it's called Gorilla Glass? Other than a marketing gimmick, of course. It's a very good one, by the way. Anybody know why it's called Gorilla Glass? Strength, yes. Thanks, John. Strength, toughness. And the story goes that back in the 1960s, Corning Incorporated in New York State in the US, developed a glass that was incredibly tough and had a very high strength, but particularly the toughness was high. And this was done by a process called ion exchange, where you essentially make the glass and then you dip it in a bath of molten salt. Potassium ions migrate into the glass from the molten salt. Sodium ions migrate out into the salt. So what you've done is you've essentially stuffed really big atoms into small holes, and this creates a compressive stress layer at the very surface of the glass. So that compressive stress layer acts to force closed any cracks or defects that develop, and in so doing massively increase the toughness of the glass. Although anybody who's taught undergraduates or probably has kids will tell us it's entirely possible to break Gorilla Glass. The number of dropped phones with smashed screens that people have illustrates that. But interestingly, back in the 60s, Corning didn't have a use for it. So the story goes that they basically shelved it, and they said, well, hang on to that for later. You never know when it might come in useful. So when, 20, 30 years later, when Apple came calling, yeah, we've got something that might just do the trick there. And obviously Corning have benefited very much from Gorilla Glass and its wide uses. And it's gone on even further now. They're producing this stuff called willow glass, which is incredibly thin glass, and that's made by a new process like down draw, where you have a trough and basically the glass fills the trough and then it runs down the sides of the trough and you draw it down into this sheet. You get incredibly thin glass there. Okay, I'm going to talk very briefly about the environment now. You remember I mentioned the forest glasses earlier. Well, the glass industry, the world glass industry, is one of the so-called foundation industries, which are major emitters of CO2. And part of the international efforts to reduce CO2 emissions, and indeed legally binding objectives in this country and others, mean that these foundation industries need to decarbonize. And one of the projects we've been looking at goes all the way, This is what happens when you've talked for an hour. Yeah, one of the projects we've been working on goes all the way back to these forest glasses, where they were called forest glasses, by the way, because ridiculously large swathes of forest were chopped down in order to burn the trees to make the ash to make this glass, which is, you know, would never be allowed today, but back in the Middle Ages, it was widely done. But you may or may not know that a large power station not too far from Sheffield is now running pretty much entirely on these things, wood pellets. Now, they're still producing ash, as are many other biomass power plants these days. They're still producing ashes, and one of the projects we're engaged in is looking at some of these ashes and asking the question, are they potential raw materials for manufacturing modern glass? So this really is 1,000 plus year old glass technology, but we're trying to bring it into the modern world. In so doing, we can offset a lot of the carbonate raw materials that are currently used to make glass, and also offset some of the CO2 emissions in firing the furnace at the same time. So provided we get this to work, and there are some very positive signs, there could be a major impact on reducing the CO2 from the glass industry. Another project related to this that we've worked on is looking at, can we actually stuff carbon into glass, almost like CCS type technology? Well, interestingly, there's some tantalizing evidence from the geological literature that yes, indeed you can. And another project we've been engaged in, we've been looking at trying to increase the CO2 solubility, a bit like sugar in tea, dissolving it within the glass during melting. The key is you have to apply very high pressures, but it's never really been tried before at lower to intermediate pressures. But what if you could get 2, 3, 4, 5, 10% CO2 as an actual constituent of the glass by applying a technologically viable pressure during melting? And we've got some early results which indicate that not only can we get several percent, this is taken from a publication that's not mine, I must add, this is not our work. This is one of our collaborators. But there are some tantalizing evidence that indeed that could be the case. And not only that, but you might get some interesting properties alongside that. So a potential CCS route, who knows? We've also been working on radiation resistant glasses. So these are glasses that resist radiation in extreme environments. They might be nuclear environments, they might be space, or other high radiation environments. So I don't know if you can see this image, but this is our base glass that's been exposed to X-rays. You can see it's gone very, very dark in color. But with our little sprinklings of fairy dust, we've been able to develop a series of glasses that, whilst the discoloration isn't zero, it's still considerably lower than the corresponding so-called base glass. So we've been developing new glasses that potentially could be used in high radiation environments as well. Okay, so just to finish off, coming back to the original title, to ubiquity, and let's use Buzz Lightyear's phrase, to ubiquity and beyond, and let's go beyond the present. So first of all, here is an inexhaustive image of some of the things we use glass for in the modern world, everything from radioactive waste immobilization to wind turbine blades, fiber optics, mobile phones yet again, architecture, etc. But what about the future? Well, here are some more crazy and less crazy potential future options. The glass plane is something I would never get on, but nonetheless. And glass science, we're now able to image atoms. This is a photo that was taken of some crud, it was called, on an electron microscope a few years ago, and it happens to have proved a 70-year-old theory on the atomic structure of glass. Turns out that the gentleman was spot on many, many, many years ago. And let me just check the chat. I suspect I'm running out of time. Yeah, I am. Okay, so I'm going to just finish up with a few acknowledgements. Thank you to everybody for inviting me and for funding and for your attention, and cheers.
Well, thank you. Well, we can't hear a round of applause, Paul, but thank you very much for that very interesting and engaging talk. There's been a few questions put in the Q&A. We've only got a few, so if anybody's got one they want to throw in the next few minutes, please do so. I suppose the first question that came in very early in his talk was, is glass a suitable material for additive manufacture?
Well, that's a good question. In principle, yes. And, 3D printing and additive manufacture of glass in the last few years, 2, 3, 4 years, there have been some real advances. But one of the issues with it is that it tends to use a wet chemical process for the precursor materials and potentially generates an awful lot of potentially hazardous waste. So in principle, yes, but I think it's not necessarily going to be as simple as those who are kind of pushing that technology would have us believe. There may be waste streams that are in very high volumes that need dealing with.
Okay. There's a question about the Murano island. Why did that become so famous in the sort of 1600s? What was the actual technology they had?
Well, I mean, some of the recipes have never been shared, but I think what it was the purity of the raw materials first and foremost. If it doesn't matter which combination of sodium and silicon you use, if you've got, say, too much iron in your sand, or you've got too many transition metals. So fundamentally it was the raw materials and the sources of raw materials. But also, of course, it was part of the Venetian Empire, probably one of the greatest trading empires the world has ever seen. So that undoubtedly played a role as well.
Okay. I've got a question from myself, actually. I make some parts at the company I work for that go into crushing up old glass, and they're very, very scared about nickel contamination. What is it about nickel that is bad for glass?
Right, nickel is a problem because it can cause something called nickel sulfide inclusions, and there have been some of these high profile cases where panels on expensive posh architecture have spontaneously broken or exploded or fallen off, and often what that's caused by is a nickel sulfide inclusion. So if you've got nickel that goes into the furnace, it can form a nickel sulfide, which basically balls up, forms a sphere in the glass, and you get a very big tensile mismatch. That's not the word. Tensile stress setup, which means that it can potentially be released, and then the glass plane will smash, and you've got lawsuits and court cases, and the media love it, and so that's why nickel is considered bad, particularly for architectural glass. But maybe a bit less bad for containers and bottles and so on.
Okay. Yeah, I think it's plate glass manufacture. So,
yeah.
Another question is, at the moment we hear a lot about obviously the glass being used for the containing the coronavirus vaccine, and how it's very difficult and to make and quite rare. What is it about this glass that's so critical? Obviously, it's a hot topic at the moment.
Well, Pyrex type glass, borosilicate glass, is widely known as being it's used for a lot of medical vials. It's used in laboratory ware. The main reason it's used for those things is that it's incredibly chemically resistant, and other grades of glass even are less chemically resistant than Pyrex and those types of glass, borosilicate. So for medicinal vials, and particularly vials of things like the COVID vaccine, I've not actually come across this story myself, Andrew, so I'll be Googling it after this call, but generally that's why they use those types of glass, because of the inertness of it relative to the things that it's containing.
Okay, I think one last question. There was a question about whether the ash from places like Drax has been trialed as a raw material in the power station for glass. You talked about the forest glass, whether the ash was considered to be used in modern manufacture.
Yes. So that sorry, I was just looking at the I was trying to multitask. That that is an ongoing project, actually. So, I mean, I gave Drax as one example, but what we're doing is we're looking at biomass ashes from across the UK, and there are, a growing number of biomass plants. And one of the products that we're looking at potentially using it in is glass. And we've done quite a bit of work in the lab, which shows that, you can put 5, 10, 15 weight% of some of these ashes as a raw material into commercial type glass, so the kind of stuff you see in your jars and bottles and so on, quite successfully. We've done larger scale melting trials. One of the key issues is around consistency of sourcing, and that's something that we're looking at the moment. But if we can get it to work, then you've got a new supply chain for waste, some of which is currently being landfilled. You're offsetting carbon, you're offsetting man-made raw materials as well. So there's a lot of wins there if we can get it to work. Excellent.
Well, I think that's exhausted the questions that people have put in the Q&A function. So I'd like to hand over to Mark Tomlinson, who's our secretary, to give the vote of thanks for tonight's lecture.
Sorry, am I on?
Yeah, we can hear you.
Okay, right. So thank you very much for a really fascinating talk. It's been excellent to be taken on a 2,000-year journey that's been really entertaining and also quite interactive with the audience. That's been really good. I'm sure we're all looking forward to it coming to BBC Two in the near future. That was a really good investigation into both the science behind glass and a number of modern applications and manufacturing methods. It's really good to have a bit of chemistry thrown in there. Learned all about silicon and sodium and calcium, lead crystal, and tin. And speaking of tin, we've got our traditional gift for our speakers. I hope it's made its way through to you already. It's unfortunately not a glass that you can fill, but it does the job anyway. So on behalf of everyone here tonight, I'd like to say thank you very much for a fantastic talk.
Well, thank you very much, Mark. It's been my honor, my pleasure.